All right, so I'd like to welcome this evening Professor Sergei Gulyaev, who's AUT professor and also director of the Institute of Radio Astronomy and Space Research, and a great friend and supporter of the Society. So thanks very much for coming along, Sergei.
Thank you, everyone. Yes, thank you for inviting me to talk about it. And, not about it. I could choose any topic. And then I thought, for many years I thought about this, synergy, music and astronomy. And I had some thoughts and had some research which I never published in this area. And maybe I should collect things together and even bring my violin and show some intervals and some chords and some things. And I told Bill about this topic, music and astronomy, and then I thought, no, it had to be music and cosmos probably. And then, on the second thought, I think that's about me, about my life, music and astronomy. And it was like, they gave this great picture, but this is me too. So, yeah. So it's about my life, and I think maybe I play something. Oh, we don't have. Yep, it will work. Too loud. Okay, enough. Thank you. I'm glad that you can hear it, because I worried that should I take amplifier or just play it as it is. It's a nice violin, Steiner 1760 something. Very nice one, but I spoiled it a little bit on purpose. You can move a little bit the bridge, and everything will change. And it has very bright concert, sound. You can go to stage, big stage, and you will hear it from everywhere. But I, on purpose, change it to more jazzy sound, like it's a little bit husky. So, yeah. Right. What do I have next? Right. Music and astronomy. And I will talk about several things. For example, these gravitational waves. Like, they go slowly, these two black holes or two neutron stars, and then faster, these waves. And if you imagine these waves in terms of sound, it will be something going higher. And then the final thing is, they call it the ring, where absolute very high sound. And I will try to show you, maybe. But slowly. the ring, gravitational waves. And I mentioned here Doppler shift. I illustrated to my students with sounds, but I sing, but now I can play. I have violin. I say, imagine you're standing by the highway, and the cars go. And when they approach you, that's the blue shift. And when you go away, it's a red shift. So the frequency is higher here, and it is lower there. Normally, if it doesn't go, it would sound something like. But when it approaches you and then goes away, it sounds like this. One car after another. Is it similar? Yeah. Oh, no, normally I do it with voice. Doppler shift. Some more examples, of course. Pulsars. When I look at this PP dot diagram for pulsars, that's analog of Hertzsprung-Russell HR diagram. And William van Straten, who is sitting here, our associate professor, he gave me this beautiful picture. And I think about these periods of pulsars. You know, when you have pulsars with a period of 1 second or half a second, it's like or faster. But when you come to these periods of 1/100th of a second, that's a frequency of 100 hertz, and 1,000th is 1,000 hertz. And here, each millisecond pulsar for me is music. It's like another one. Another one. And there are no faster. The highest, I think, is 6 or 3 milliseconds or something, and it is like 700 hertz. 700 hertz. Yeah. So, right, this is 880. So 700 would be. That's the fastest millisecond pulsar. What else? I thought resonances. Of course, we will talk about resonances between planets, their orbital motion, their spin, their rotation around their rotational axis, and orbit around the sun, for example, or moons with respect to planets and with respect to each other, and asteroids and rings. And we'll talk about, if we have time, Lindblad resonance, origin of spiral arms in our galaxy. What are these resonances? Resonances are a ratio of frequencies or periods which can be presented with integer numbers, like 2 to 1, or 3 to 2, or 4 to 3, or 5 to 4, 6 to 5. And okay. That's from my end. Maybe before I go to this, I can say that we have it all in music. And I will show you, because 2 to 1 is an octave. That's octave. And 3 to 2 is the fifth. And the fifth is how we tune the violin. I think I tuned it nicely today. And the fourth would be. this is ratio of 4:3. And the third, major third, this is minor third. They're a ratio of 5:4, 6:5. We have it everywhere in music, and these intervals make music consonances. They make these intervals sound beautifully, and chords sound beautifully, and all these things, and it's not dissonance. But of course, composers use everything. Last year, I gave this lecture, Golden Age of Radio Astronomy, and I started from introducing this electromagnetic spectrum, and this is like visible light, and this is area of radio astronomy. And I said that visible light, you know, this wavelength is just a ratio of 2:1. Yeah, that's just 1 octave. And the whole beauty of the universe, whole rainbow, is just 1 octave in music. Radio astronomy, it's grand piano and even more. So I wanted to say that radio astronomy is so great.
Is that your piano?
No, I don't. I'd wish.
Does your family have a grand piano?
Sorry, just let me finish. And here I introduce the piano and its octaves from 0 to, and then I had no place, and some have 8. This is 12 ET. Actually, it is TET, but I like more ET without the first letter T. So 12 ET, and it is equal temperament. It is actually, this is a logarithmic scale in terms of frequency, and it is divided all very equally. And let me show you. In terms of hertz and frequency of sounds, this is A of the 4th octave, and the frequency is 440, 220. So ratio 2:1, 2:1, 2:1, 2:1. Always we go with this progression. And this represents a logarithmic scale. And in 1 octave, we have 12 semitones, and they should be, all these differences should be all different. Because imagine here we're just talking about a few hertz, but here we talk about tens of hertz for each semitone. So there should be equal distribution of them in terms of logarithmic scale. That's very important. And the formula for this is well, I could start from anything, but if you use n number indicated here, then there would be for note A of any octave, you just substitute n here and you have A. We deal with logarithmic scale everywhere. Decibels in acoustics and electronics, that's ratio of power. And here is ratio in terms of decibels. It's how we perceive the sound. This is what we measure with devices, and this is how we feel. Stellar magnitudes, this is flux density, what we measure with our devices, and this is what we see with our eyes. And here we come to the so-called Weber-Fechner law. Psychophysics law relates to human perception. More specifically, the relation between the actual change in a physical stimulus, this power, flux density, and so on, and the perceived change. This includes stimuli, okay, to all senses, please correct me. Vision, hearing, taste, touch, and smell. I don't know, maybe even love. It's also sense. And yeah. And it says that if things change like by order of magnitude, you feel that it is just maybe a little bit more. Another order of magnitude, a little bit more in terms of love. Someone loves you order of magnitude more, but you feel that maybe it's just a little bit more. And this is where this logarithm comes from. If you integrate both sides, this is for mathematicians, you will have logarithm and immediately. And it brings me to this redshift. Actually, change in redshift is equal to df over f. So we come to the same logarithmic scale. And in terms of the redshift, actually I said octave is 2 to 1. If you have a redshift z equal to 1, it is an octave in terms of frequency. Redshift 0.5, it is the fifths in music. So if you have one object here that sounds like this, the redshifted 0.5 would be this. And the redshift 1 would give you exact octave from this to this. And so on. You can, but I should say that all these are analogies. This is like with redshift, we talk about electromagnetic waves and change in frequency of electromagnetic waves. But when the car was moving, that was sound. That was waves of in the air, propagating in the air. So yeah, also redshift. Once I walked in Mission Bay, and there is a big hill there. I don't know how it's called. And people show each other these airplane models. And they keep them with the rope, and they go around and around. You probably saw these models of airplanes. And I walk, and I hear it just goes. I thought, okay, this is major third. So I walked and I calculated in my mind, I had no piece of paper or something, what was the speed of this device. And actually, I did it. So for those who teaches physics, William teaches physics, we can think about this problem for our students. Yeah. Right. So this is a calculation of each frequency. It is here. You can see 440 hertz for A. And here, if you go lower, 220, 110, 55. And you can calculate all this using this equation, and n over 12 semitones, and n changes from 0 to 12, and then the new octave starts, from 1 to 12. So there are 12 semitones, and you can do this calculation. 440, I was interested. I think maybe you will be interested also. That's concert pitch, Stuttgart pitch. And there was international conference in Stuttgart, and they decided that A should be tuned to 440 hertz. If we go to the internet now and find 440 hertz, it would sound probably like this. And then it became the technical standard, and there is international standardization organization, ISO, and according to their verdict number 16, it became international standard, but Philharmonic orchestras, they ignore these things slightly. for example, Berlin Philharmonic now use 443, which sounds a little bit higher. And the highest pitch is in Vienna Opera, 445. And I checked La Scala pitch, and it was the same as in Bolshoi, 442. Modern ensembles, which specialize in performance of Baroque music, they agreed to the standard of 415 hertz. So it sounds like half a tone lower. Not this, but this. And the whole music, you just have your music sheet, and you tune your instruments half a tone lower, and that's Bach pitch. A Mozart pitch was something between. So now most of us use 440. Yes, I'm not sure about Auckland Philharmonic Orchestra. They probably follow most of Europeans, 442. It depends on oboe and how it's tuned. Right, that's what I told you already. Octave 2 over 1, fifth, 3 over 2, fourth, third major, third minor. And I have to go to the Excel table that I did. And I hope you will be able to see it. Right, so what we see, I just calculated this n from 0 to 12. And 0, it is like the ratio is 1. For example, you can take 440, and then in order to get each next semitone, you just multiply 440 by this, and this, and this, and this, and you go. And you will have this ratios of semitones to the initial one that you start from. Okay, and what we want to have this music sound beautifully, to have this consonance, to have this exact ratio, exact ratios 2 to 1, 2, or 5 to 3, or 3 to 2, 1.5, 5 to 4, and so on. Here, exact ratio. We call it Pythagorean temperament, when all these ratios are pure. And this is what we have on piano, for example. That's equal temperament. And we can compare them. They're pretty close. Look, here we have 1.6, here 58, 59. Here, yeah, 1.2, here 1.18, 19. And in music, we use the notion of cent. Where can you go from dollar? Cent. Cent is 1/100th of semitone. And I calculated this deviation in cents. So no deviation, of course, in octave. And here, the most important intervals, the fifth has deviation of something like 2 cents, and 2 cents for fourth. And here for minor and major 6 and minor and major third, we have quite significant deviation, 13, 15, 16 cents. But can we feel this? And some people say that they can feel something like 2, 3 cents. I don't believe it. The best musicians report that they can hear 5, 6 cents difference. But like more or less a normal person can feel quite easily something like 10, 12 cents. So this deviation in cents is quite significant if you go for equal temperament. And composers, good composers, when they compose plays for piano, for example, they know that this is equal temperament, and they go around this. They normally don't allow this interval sound together. That's why piano sounds so when it is composed with a good pianist, a good composer. Yeah. Right. Maybe I go back to my slides. Right, so 12 ET, equal temperament. Should we try something else? Maybe not 12 semitones, but I don't know. For example, Arab quarter tone scale, 24 ET. And here, can you hear the difference? Quarter tone, yeah, definitely. Okay, and so on. Or, for example, Nicola Vicentino in the 16th century invented this instrument, which has, you see how many keys, and it's called Archicembalo, 31 semitones in one octave. And you can find in YouTube how it sounds. It sounds very, very nice, very pure, very interesting. Yeah, maybe music of the future, but oh, what can be more beautiful than piano? And when we talk about tuning of piano, this is whole art. And these people who do this tuning, experts, it is art of tuning. They listen for what we call beats. In physics, we know that when we have two waves which have close frequency, we hear some extra frequency, and they rely on this. Well, they go with some other approaches, and here it shows this keys in major, and then keys in minor, and basically you cover all 24 possible keys in minor and major. And of course, Bach was absolute genius. He created music for harpsichord. Do I pronounce correctly? Yeah. And clavichord. And of course, for organ. And this music was for instruments which are tuned in equal temperament. Actually, you can read sometimes about just temperament. And what you can read that, oh, just temperament is not exactly as equal temperament. And this is all. They don't explain what's the difference. So I suspect that this is the same. But maybe musicians will correct me. I look at my friend Herschel, who is a great musician. Oh, and here we have Bach in his older ages, but he wrote this foil temperire clavier, or well-tempered clavier, in the age of 38. So he looked like this, actually. And he wrote for organ. Look at this device. Oh, gosh, this is again, each organ is just, I don't know what to compare it with some Sacrata Familia, maybe some amazing piece of art. Yeah, and look at this. This is like in spaceship. And he uses everything. And these tubes, each of them is tuned very carefully. So it all equal temperament again. And Bach knew how to make it sound beautifully. And right. Okay. No. Okay. Okay. I thought that I have another slide here, but let me go in this sequence. So basically, equal temperament is realized with this fretted instruments, but some people prefer fretless or unfretted instruments, and they can do nicer, if they are very high expert, they can do very nice intervals with them. And string quartet, oh yes, because string instruments, this two violins, one, oh, very special viola amati. We have it in Auckland chamber, in New Zealand chamber orchestra, this one. Here it is. And cello. So how they tune? So we know that we have perfect fifths for the violin. Viola is tuned starting from the next string, not E, but from A. And one fifth lower. And then as we come to cello, it is tuned exactly as viola, but one octave lower. So it creates perfect mathematical situation when you can reach all these perfect intervals and chords with one ensemble. I discovered, shame on me, I didn't know about Alfred Hill. He is a great New Zealand composer. He wrote huge amount of music. He lived from 1869 to 1960, a long life. So it just struck me that he was teenager, he was a young man when it was, Tchaikovsky and Verdi and Puccini and then all these 20th century composers, and he wrote his music, and we can be very proud of him. Let me show just a piece of his string quartet. Yeah, maybe just from here. And you will hear these beautiful intervals he uses with string quartet. How beautifully, just perfect intervals, perfect chords. I should click here. Yeah, and there are many discs with him. He wrote, I think, something like 18 quartets. and human voice, of course. And I have here our Kiri Tikanov and Malvina Major. I couldn't find them singing, the sound recording, but I found equally beautiful one from Sydney Opera. That's Flower Duet. Listen to these intervals. And this is, you will recognize just the beginning, very beginning. And that's beautiful ensemble of voices because yes, in terms. Right. About the beats, you see, if you have two close frequencies, you have this pattern, and obviously one more frequency, some appears in addition to some high notes, and composers like Bach knew it so well. And just listen a little bit. Interval, but it creates this beat which makes it like they call it vox celesta or something that makes you just some people just get fainted or yeah. And interestingly, I found the same toccata and fugue D in D performed by quartet. And look at this end, and they can't do it. It sounds perfect, but we lose so much. We lose this vox celesta. heavenly voice. But organ makes so many colors. Right, so we talked about planets and their resonances, and the famous Laplace resonance is the periods of three Galilean moons of Jupiter, Io, Europa, and Ganymede are perfectly aligned in octaves. 2 to 1, 4 to 1, and they sound absolutely perfect. And the resonance 2 to 3 between Pluto and Neptune, it means Pluto completes 2 orbits in the time it makes Neptune to complete 3 orbits. And this is in the reference frame connected with Neptune. So if Neptune stays, then other planets would do these motions around. And you can see this fantastic motion of Pluto that it makes. And actually, this resonance makes Pluto stable on its orbit. Well, at least for the next millions of years, it will be there because of this resonance. Actually, Isaac Newton, who created the gravity theory, he also created the perturbation theory, and he applied it along with calculus to stability of the solar system. And the problem was this. Okay, we have this very massive sun, the sun sitting in the center, like 99% of all solar system mass is in the sun. We have Jupiter, which has mass 1,000th of mass of the sun. And then we have little rocks like Mercury, Venus, Earth, Mars going around. And can we find whether Jupiter can disturb the motion of these planets? And he found, using his perturbation theory, that the solar system can be stable on the time scale, which is the period of Jupiter, 12 years, times the ratio of masses of the sun to the mass of Jupiter, which is 1,000. So 12 times 1,000, 12,000. After that, this perturbation should be so big that all these planets will go away. They don't. So he came to the idea of the divine watchmaker who comes every, say, 10, 12,000 years and makes this clock moving correctly again.
It's interesting with Pluto and Neptune because Pluto's orbit crosses Neptune's orbit, but the resonance means that the two planets never approach closely.
Yes.
And that's what makes it a stable situation.
Yes,
Because
exactly.
the inclination is so different.
And inclination, we will talk about inclination later. Some other resonances of trans-Neptunian objects. 1 to 1 for Trojans, 3 to 5, 4 to 7, 1 to 2, Tutinos they're called. 2 to 5 resonances with respect to Neptune. Another resonance, very interesting resonance for the pulsar. His name is Voschang. What's his first name? Alex Voschang. That's the guy who works with William. He discovered this, this pulsar with 3 planets. And they have periods which have this beautiful musical resonance. So the planet A, B, C, their frequency or periods ratios is 8 to 3, 3 to 2, 4 to 1. Their integer numbers. Actually, a very interesting interval that I didn't mention is called tritone. It is exactly the 6 in the middle. So you start the octave, you have the beginning and the end, exactly in the middle, number 6. And you can calculate, see, 2 to the power of 6 over 12. 6 over 12 is what? Half. 2 to the power of half. It is square root of 2. It is one of the greatest examples of irrational number, which never can be presented as a ratio of integers. And you can hear how this tritone sound. This is square root of 2. The sound of the square root of 2. And some other resonances between different moons of Jupiter. 3 over 2 is fifths. This is the fourth. This is octave again. They like octave very much. Resonances can be stabilizing and can be destabilizing. Stabilizing resonance is in Pluto, and it allows life. Destabilizing in Kuiper belt union objects that shows their positions. And here is resonance with Jupiter 3 over 2. Oh, sorry, this is asteroid belt. This is not Kuiper belt. Asteroid belt between Jupiter and Mars. And of course, influence of Jupiter. It throws away everyone who has this ratio of periods of frequencies with Jupiter, and throws away these guys. And these guys just cannot exist. Destabilizing resonance. Trans-Neptunian objects that I thought that I showed this, and Pluto is here. And here it shows inclination of Pluto, something like 17 degrees, I think. Something like 17 degrees. And here resonances. Red shows resonances. And resonances are 2 to 3. 3 over 2, it's the fifths. And some other octave. 4, 3, 5 over 4, and so on and so on. That's very interesting example of resonance. The Earth is here, the Sun is here, and this is a frame connected with the Earth. So the planet is doing this. Each year it's doing this, and it shifts and shifts and shifts and shifts and shifts and shifts. And in 100 years it reaches this point, and then goes back, and then again another 100 years. Amazing. That's another example of asteroid. Saturn with its rings. That's beautiful photo. The Sun is behind, and so we can see all these Saturn rings. Look at this. I think, 2 moons of Saturn, along with Epimetheus. Janus acts as a shepherd moon, maintaining the sharp outer edge of the A ring in a 7 to 6 orbital resonance. That's their motion in the frame connected with rotating Saturn. So it goes slower, 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 and then faster, 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 and then slower, 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 and then faster, faster, when they meet together. And this one, opposite direction. That's how they move. And, another resonance. I'm just a little bit, I know that time, I need another 5 minutes.
No, that's fine.
Okay, another resonance, incredible, 10 to 11, and I don't know what it is in music. Modern composers like maybe Schoenberg or Hindemith or Schnittke or and 7/6. I think it is, yeah, the second, yeah, major second. And this is Saturn rings form 2/1 orbital resonance with Janus. Jupiter's rings. That's a very interesting example. Jupiter and Greeks and Trojans here, and asteroid belt, and consonances everywhere. Now, in that little text that I submitted to Bill, and they published it in the journal, that we will play the music melody of the solar system. So let me go to another Excel table. So please try, follow me, and we need a little bit of focus. So we have planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, even Pluto I included. Fine. Yeah. Sorry, astronomers. Yeah. Orbital periods: days, years. In seconds, I changed periods into seconds. And in order to find frequency, I just take 1 divided by this period in seconds, and I get this. But, you know, in music, you can play a melody in 1 octave, and you can play higher, and even higher. So it just change from octave to octave. So I did it. I changed from octave to octave, and I found the hertz, this frequency in hertz, which corresponds to our ear capacity. And you can see here that I had to multiply by 2 to the power of 32. So 32 octaves. Is it called transposition?
Yeah, transpose.
Transpose 32 octaves from this heavenly organ, our solar system, to what we could hear with our ear. I had some frequency, and I did it for each of them. And then I calculated again frequencies of different tones. And I enumerated them, and here I wrote which tone it corresponds to. So I had notes for planets. Should we try and play it? So C sharp, A, C sharp again, D, F sharp, D, G sharp, and C sharp. And of course, I could transpose it 1 more octave higher or 1 more octave lower. So I don't know. Maybe I need to play some ideas. So C sharp, okay, that's Mercury. Venus. Again, Mercury. And then, yes, and then Earth also. And maybe. And then Mars. And then Jupiter, Saturn. And then Uranus and Neptune. Nice. And I think it is attributed to the famous Titius Bode law, which also has this 2 to the power of n, this octave things. So it is beautifully tuned. I don't see any dissonance here. We can play it in a different way. Something like this. And yeah. Aha. And it brings us to the end. I forgot where I should start. Not from the beginning, definitely. Thank you.
Well, thanks very much, Sergei.
Yep.
Have we got any questions? Herschel.
So in the ancient Greeks, they talked about the music and the spheres. Do you know much? And then Kepler.
Kepler, yeah.
I don't know much more other than what I just said, so maybe you know something about that.
I looked honestly at the ideas of Kepler, and I thought that he would do what I did, just having periods, go to frequencies and sound. But no, he did it differently. He was absolutely obsessed with his laws, where planets move in ellipses, and there are differences between, apogee and ephelium and perihelium, and he somehow started playing around this. So for me, it doesn't have a good foundation, because basically planets' orbits are more or less circular, except maybe Mercury and Mars.
In other words, he didn't take an average of the ellipse.
What he did, I don't remember, but he had some mathematical procedure which is not convincing to me. Okay. Sorry, Kepler.
I looked at his book. I read through it, but it didn't mean. I don't know.
Yeah, you also did.
Like
you also didn't understand. Yes.
But I think, doesn't that idea go back to Pythagoras?
Yeah, I think so.
So, wasn't he the first person to sort of talk about the music of the spheres? So, yeah, and I saw that one of your slides you mentioned that, the Pythagorean temperament. So, yeah, I wonder if you've got any thoughts about Pythagoras?
Yeah. Basically, the string quartet, it follows this Pythagoras temperament. And it makes it sound so incredibly. And look at this Alfred Hill quartets. Do listen them. They're incredible. I listened 3 or 4, and they all were fantastic. Wow. It was like, wow.
Is it on YouTube?
On YouTube, yeah. And I wonder if he is some relationship with Michael Hill, who organizes violin competitions in New Zealand.
One thing about Pythagoras, he came up with these ratios, but he
Yes.
wouldn't have had any way to measure frequency, so he could only hear, which is a logarithmic scale.
Yeah.
So I wonder how he figured out the ratio of frequencies.
I'm not sure. You know, it's history of mathematics. When these logarithms were invented, I'm not sure. You guys probably know. I should check, but thank you for this comment.
You had an example of the Arabic
Yeah.
structure there, but also the Chinese music octave is different again.
Chinese is interesting. It is so-called pentatonica, and they just have five notes in the octave, and they play around them. But of course, modern music is absolutely different. And with this unfretted instruments, you can do infinite number of how many? It's like Professor Higgins asked Eliza Doolett, how many?
There was a speaker we had a few years ago who had been doing simulations of various different kinds of solar systems.
A lady?
And I can't remember who it was, but
Young
they
lady.
converted somehow had a method of converting the orbital motion of the solar systems into sound. It was quite interesting when the solar system went unstable, like for ours for the late heavy bombardment, everything suddenly becomes discordant and really angry sounding, and then it sort of settles down again. It was very interesting.
The solar system presents an example of chaos. We cannot predict what will happen with it in 10 million years. Well, predict with our mathematics. And by the way, Mercury has very interesting resonance with Jupiter. And I read somewhere that Mercury may be unstable in a few million years and goes away from the solar system. So we need to start studying Mercury as soon as possible, like that iron-nickel asteroid, rusty asteroid.
We got a couple of questions from the internet, well, all from one person, Mitchell Clark. So he says, Kira Sergei, sorry I missed the first 30 minutes. Did you talk about 12 ET as a compromise?
ET is well, mathematically there is no way of making temperament that would be ideal for these fretted instruments. You cannot tune piano that and get perfect intervals. No temperament. So mathematically, it is not solvable problem. That's probably my answer.
And Mitchell also says, do you think if you had enough planets in orbital resonance, you could approach the celestial equivalent of a Wolf interval?
Oh gosh, yeah, I read about it something. Actually, when I prepared to this lecture, I discovered tons of literature. And I was just in my ups and downs, and at some stage, no, I should call Bill and say, Bill, this is enormous area. I cannot know everything. And here this question where I'm sorry.
You did well.
Yeah. I will check it later.
Are there any more questions before we finish with supper? Okay, well, thanks again, Sergei, for a wonderful...
Thank you.